Greetings and welcome. In today's video we are going to continue looking at factoring, and specifically we're going to be looking at sum and difference of cubes. In which, just as a quick recall, we've already dealt with the difference of squares pattern. Which was this, a squared minus b squared, factored to be the sum and difference pattern, a plus b times a minus b. And as long as I have two terms being subtracted, both of which are perfect squares, I was able to use this pattern. I do want to point out, just as a pitfall, sum of squares does not exist. There's no such thing as an a squared plus b squared being some factored expression. So this does not work. So I don't want to indicate that since there's a sum and difference of cubes pattern, that is a possibility. So regarding sum and difference of cubes, sum of cubes would look like this, where I've basically got two perfect cubes being added together, and what that will equal when factored is a plus b times a squared minus ab plus b squared. And so that's the sum of cubes pattern. The nice thing about it is I only have to verify that the first term and last term are in fact perfect cubes. Unlike perfect square trinomials, I don't have to verify the middle 2ab term or anything like that. And once I know a and b, I can just plug it in directly. One thing I just want to point out is that for the sum, all of the signs are positive except for the second or the first sign in the second expression. Well, I guess technically second sign because it's positive here, isn't it? So yeah, so there's the sum of cubes pattern, and then the difference of cubes is very similar. Usually I memorize them as a pair, and you'll see why in a moment. This one, just a couple of the signs change, so the first set of parentheses would be negative, and in this one these will all be plus signs. So here are our two new patterns today. So we haven't seen these ones before. The previous patterns we dealt with when dealing with special products, but these ones we haven't directly seen. And then I guess I might as well also give you a list of what are the perfect cubes, but maybe give you perfect squares first. So 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 25, 36, 49, etc. And perfect cubes are numbers that are formed by the product of a number by itself 3 times, essentially. So 1 times 1 times 1 is 1. 2 times 2 is 4, times another 2 is 8. 3 cubed would be 27. 4 cubed is 64. 5 cubed is 125. And so on. So those are the perfect cubes. So as far as numbers go that I'm trying to fit into this pattern, those are the ones that I'll want to kind of keep my eye out for. So let's actually get an example done here. So if I want to factor the expression, let's say I have x cubed plus 8. The first thing I would do, I suspect that this is a sum of cubes pattern because this is a perfect cube, and 8, I believe, can be written as 2 cubed. Right? It's 2 cubed on the list there. So a would be x, and b would be 2, according to the pattern. And now I simply just plug it into the right-hand side of the pattern up here. So it would be a plus b is x plus 2. Times a squared is x squared minus ab, so that's minus 2x, plus b squared, 2 squared is 4. And in this case I simplified it kind of all in one go, but other times you might want to kind of substitute in parentheses for some of these values, just to be careful with potential more signs. But my A and B were pretty simple in this case, so it's not that difficult. So let's do another example. What if I had, let's say I've got 125x cubed minus, let's say I've got 64y cubed. So in this case, A would be the cubed root of this term. So that would be 5x, because 5 cubed is 125, x cubed is x cubed. And B would be, 4y. 4 times 4 is 16, times another 4 is 64. So now that I've picked A and B, I can plug it into the right-hand side of the pattern. I also want to point out this is the minus pattern. So I actually don't include this sign in the term for B, although technically you can use the positive pattern if you define B as a negative. But that would just require a lot more sign work and more work than we'd want to do. So it'll be A minus B, so 5x minus 4y, close parentheses, multiplied by A squared, so that's 5x all squared, and this is where I'm going to actually write an extra step out, plus AB, so that's 5x times 4y, plus B squared, so that's 4y squared. And so now we can simplify this, so 5x minus 4y times, remember that I am allowed to distribute an exponent over multiplication, so I'm squaring both the coefficient and the variable. 5 squared, 25, x squared, plus 5 times 4 is 20, xy, and square both of these would be 16y squared. Okay, so not too difficult, and then let's try one more like this, where I just kind of combine some of the concepts here. Actually, what if I've got, let's say, x to the 6th minus 1. So this, in its current form, I don't have a difference of sixths pattern, although 1 is a perfect sixth, and so is the first term. But I can pretend or imagine this as a difference of cubes. Technically, I could also imagine it as a difference of squares. But let's try a difference of cubes first. So what cubed is x to the 6th? Well, that would be x squared. And what cubed is 1? Well, that would be 1. So in this case, my A would be an x squared, and my B would be 1. And let's see, this is the difference pattern. So let's plug it into the pattern. So that's x squared minus 1 times A squared would be x squared squared, plus AB, so that's x squared times 1, plus B squared, so 1 squared. And let me simplify this right set of parentheses first. So this is x to the 4th plus x squared plus 1. And actually, that, I believe, no, based on the coefficients, I don't believe it will be factorable further. But I do want to point out that sometimes you will have an expression that, when factored, can be factored further. And x squared minus 1 is actually a difference of squares pattern. So we can factor that once again using, I'll actually write that down, a squared minus b squared equals a plus b times a minus b. So I recognize that this was a perfect square and 1 is a perfect square, so it matches this pattern. Actually, maybe I'll rewrite it here for a second. So for just this side, a would be x again. Now this is a different a than the one up there. It's regarding just this expression that I'm factoring. And b would be 1. And now I'm going to plug it into this pattern here. So I'll have x plus 1 times x minus 1, and then this set of parentheses is tagging along. And if this was also factorable, I would have to take it further as well. I believe this is completely factored. So I just want to point out you can actually have nested problems where you have to continue factoring further from the inside. But that's the idea as far as using these patterns, is trying to recognize where you might have a difference of cubes or sum of cubes showing up, determine what your a and b are, and plug it into the expression. And I do just once again want to point out that there's no such thing as sum of squares. That is a non-factorable expression. And I believe that's it. Sometimes you could also have a problem where, as always for any factoring problem, maybe your first step should be yoink yoink, take out a greatest common factor if possible. And that might reveal a difference or sum of cubes as well. All right, well, thank you so much for watching, and I'll see you all later. Bye-bye.